Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is the motion of charged particles in electric fields. This is the lesson where we actually take out all of the knowledge that we've been developing over the past few lessons about electric force and electric field and electric potential energy and electric potential and all that stuff, and we put it together for some actual applications which are quite important, at least historically. And we're really going to jump right into things here. There's not much new to teach you in terms of actual content. It really is just applying what we've learned. So take a moment to pause the video, see where we're at, and then come back to us. Take a look at the questions we're going to answer, as well as where we are in the unit schedule, and what the learning goals and success criteria are. Please do that now. Okay, you're back, and let's get started. The first example or application that we're going to look at comes to us from actually, all of the examples today come to us from our textbook, Physics 12 by Nelson. The first one is in sample problem 1 in section 7.6. And this is an example of the movement of charges through an electric field, but keep this in mind, it's one where you cannot easily use force ideas. Let me explain. So it says figure 3 down here shows two small conducting spheres. You see them right here and right here. They're placed on top of insulating pucks, the idea being that they won't lose any of their charge. One puck is anchored to the surface, while the other is allowed to move freely on an air table. So they're trying to tell you here that there is no friction. Okay. The mass of the sphere and puck together is 0.15 kilograms, and the charge on each sphere is plus 3 times 10 to the negative 6 coulombs and plus 5 times 10 to the negative 9 coulombs. The two spheres are initially a quarter meter apart. How fast will the sphere be moving when they are 0.65 meters apart? So think about what's going on here. Take a moment and pause the video and ask yourself, if this puck here is anchored to the ground, let's pretend there are some bolts in there holding it in. It says will not move, and it's positively charged. But this one is free to move, and as we said, there's no friction. What's going to happen? All right, do that now. Okay, and you're back, and obviously what's going to happen, we have like charges, so according to the law of electric charges, this puck is going to experience a force to the left. Of course, the other puck will experience an equal force to the right. That's just Newton's third law. However, this one is not free to move. So what we're really concerned with is this force here, and that, of course, is an electric force. You could even calculate it. You could do, using Coulomb's law, K big Q little q over r squared. Remember, this is force, not energy. And they say in the beginning that the pucks begin 0.25 meters apart, so that should be between their centers is 0.25 meters. I'm going to write that in. I'm going to call that R1. And of course, as they begin moving, the distance increases, and soon they are 0.65 meters apart. And that's when they're asking you how fast the freely moving puck will be. So allow me to just draw in. I'll try to be faithful to the different colors here. I don't know if I'll do a very good job. Here's where the puck is going to be when it has reached a position that we understand is 0.65 meters away from the starting point. So here's the question I want to ask you. The title here is an example where you cannot easily use force ideas. Why can you not easily use force ideas to calculate how fast this charged puck will be, or this charged sphere will be moving when it gets to what I'm going to call R2 equal to 0.65 meters? Pause the video and see if you can figure that one out. All right, you're back, and let's see. Well, when you get to this final position of R2, you have a new electric force, which is KQ over R. Now this would be R2 squared, and back here we had R1 squared. So this might be at R1, we could write, and over here this is at R2. Now you can see the denominator here is smaller than it is here, so this is going to be a large force. This will be a small force, or at least smaller, so I can write this in. And up here I can write larger. Now what does this mean? It means that the force has been changing. And so as the puck moves along, the acceleration changes. Because as we know, F net equals ma. This means that if you were thinking, oh, movement through a distance, speeds, velocities, maybe I'll use this formula, v2 squared equals v1 squared plus 2a delta d. If that thought had crossed your mind and you were hoping to use the electric force to calculate the acceleration using Newton's law, well, you would be in big trouble here because the net force is not constant, and these kinematic equations deal with constant acceleration. This is why you really are going to have a hard time using force ideas if you want to solve this problem, which means you got to use some other idea. Well, the other idea that we've used in this course for predicting motion is energy. Let's see how this question pans out if we use energy ideas. So first of all, the main energy idea, of course, is the law of conservation of energy, which tells us that the total energy at point number 1 equals the total energy at point number 2. Now, the next thing we have to do is identify the forms of energy. There's going to be motion, so that is kinetic, and of course there is electrical potential energy, so that is EE. So I'll write these as EK1 and EE1, converting to EK2 and EE2. All right. Now, we're going to assume that these are point charges, which means that we can use our newly learned formula for EE, the one from a couple lessons ago. And of course, kinetic energy you already know. So what do we write in here next? A half of mv1 squared plus, now do you remember the formula for EE? It's not negative, it's rather k, big Q, little q. That'll be over the initial position. We don't need the negative in here, remember, because what we're supposed to do is include the signs in the charges here. That will take care of whether the energy is positive or negative. And that is equal to the final kinetic energy, a half mv2 squared plus k, q, big Q, little q, over r2. All right? Now, at this point, you're probably going to say, oh, I see how this is shaping up. Initially, this is not moving. I believe it says somewhere in here that the sphere is initially at rest, and then it is released and starts moving. So yeah, we're going to make a half m1 v1 squared equal to 0, but before we do that, I want to point out something that we're going to need to use in a later example, so bear with me here. If you look at this formula right here, the one that we had just one line ago, I'll try to highlight that, and allow me to just pull this down here for a moment. I'm going to rearrange this. Look what I get. I'm going to put all of the EKs on one side. So there's EK1 minus EK2. I'm going to put all the EEs on the other side, so EE2 minus EE1. Now, look what we've got here. This side is easy. Every math student should see what's going on here. It's a final value minus an initial value. That's a delta EE. What do we have here? This is an initial minus a final, which is actually the negative of EK2 minus EK1. I'm just doing a little bit of math there because I want you to see that this is the negative of a final minus initial, delta EK. So look what I get just from thinking through the law of conservation of energy. I've got this formula involving deltas, and what is this telling me? Let me just create a little bit more room. And now let's see what this means. What does it mean to say negative delta EK equals delta EE, or if you will, positive? There is really a positive in front of there, or there isn't a negative, right? This is telling me that if I lose EK, then I gain the same amount of EE. Now, this may not seem like a big deal to you. You might be thinking, oh yeah, well that's the law of conservation of energy, which you said you were using. However, keep this in mind because we are going to need this a little bit later on, all right? The loss in kinetic energy equals the gain in electrical energy Or, if you prefer, which is actually what's going on here, is that a gain in EK will be represented by a loss in EE. It doesn't matter where we put the negative, right? We could write this as delta EK equals negative delta EE, if that makes you any happier. All right? Same idea. So what's going on with these pucks? Let's get back to sample problem 1. The idea is that two positive charges which have positive EE between them, because they are like charges, they are getting farther apart, which means when this one gets to here, it has a less positive EE, the electric potential energy between the two. In other words, we will have lost EE. Think of that as negative delta EE if it makes you happy. Where did that EE go to? Law of conservation of energy tells us it's got to go somewhere. It actually goes into EK here. The puck picks up speed, gets moving faster than it was before. So now let's finally do the calculation. So what I'm going to do is I'll highlight this in blue so you can sort of keep track of where everything's going. Here's the actual calculation. Remember, a half mv1 squared was 0. K, the first Q, which doesn't matter which is which, you could call that this one. The second Q, which is this one, divided by R1, which is going to be the 0.25 meters, is going to be equal to a half of the mass. Now, what was the mass here? I think they said 0.15 kilograms times the final speed squared, plus, once again, K, big Q, little q, over R2, which is this number here, 0.65 meters. Now, I've left out the K and the Q because with scientific notation, I'm going to run out of room here. But I think you guys are going to be able to solve this because you know these three numbers, you know these three numbers, and so it shouldn't be too hard to solve for V2, the final speed. All right? Even if you get stuck, you can take a look at how the textbook does it. I just wanted to show you where everything's coming from. And I also wanted to emphasize, extremely important, if you were tempted to use force and kinematics ideas, you would have been at a loss because the kinematic ideas that we have are for uniform acceleration. And uniform acceleration can only happen if you have a constant F net. The problem with this situation is as these charges get farther and farther apart, the net force, which is the electric force here, goes from a larger value to a smaller value, so you have a problem of having to deal with changing net forces, and our formulas are not set up to do that. So we got to use energy. All right? Let's move on to another example. This one also from your textbook, Physics 12 by Nelson. This is an example where you can use force ideas. They talk about a device called a cathode ray tube. If you don't know what a cathode ray tube is, then I want you to go look that up. You would have learned about it the first time in grade 9, and now it's back. I guess it's not crucial that you understand every single detail about this, but to give you a really, really simplified idea, the idea behind a cathode ray tube is that electrons, so I'll write them as E minus like this, are going to be accelerated through a potential difference, symbol delta V, and we are going to have to repel them from one end of the apparatus and attract them toward the other. So if you think about it, if we make this end of the apparatus negatively charged, and we make this end positively charged, and the potential difference is delta V, so we may accomplish this by connecting a power supply, then the electrons will be accelerated to the other side. Now, the interesting thing in a cathode ray tube is that they often use the oppositely charged parallel plates that we discussed in the past couple videos. If you remember these, they often accomplish this by having the following setup. If you take oppositely charged parallel plates, connect them to your power supply so that the negative side is over here and the positive side is over there, then any negatively charged particle, like an electron, will be accelerated to the other side. Now, if you remember, in the oppositely charged parallel plates, there is an electric field. The electric field, by definition, is the direction that positive charges get forced. Remember the positive test charge. In this electric field here, the positive test charges would go this way. So I'll use red arrows to show the electric field, reminding you that this is how many newtons per coulomb on a positive test charge. Of course, as I mentioned, the cathode ray tube uses electrons. They're going to go the other way because of the law of electric charges. Now, do you remember the formula for the electric field? It was E, parallel plates, equals the potential difference divided by the distance separating the plates. And do you also remember that this is a uniform electric field? In a similar manner, the gravitational field that you are living in right now is also uniform. It's 9.8 near the surface of Earth, and it's pointed down. So if we have that, then we can write, just like we write Fg equals mg, what we're going to write here is Fe equals QE. These equations are analogous. So here we have a constant force. We have a situation unlike what we had here, where the force was not constant. So if you wanted, you could now use the kinematic equation ideas here. So now let's take a look at the problem and see how they ask it, how they pose the question, and therefore how we're going to answer it. They say that in the cathode ray tube, figure 4, I left out figure 4, sorry about that, found in a computer terminal or on an oscilloscope. Now, when they talk about a computer terminal, they're talking about the old style computer terminals that, you know, they take up a ton of space on your desk. They kind of look like this, kind of like the old style TVs, not the flat screens that you see these days. But anyway, an oscilloscope is a similar device. You can look these up online to find out if you don't know what they are. So it says, the cathode ray tube is heated, and what that does is it causes electrons to leave the cathode. So what happens in here is there is usually a filament, similar to a filament in a light bulb. I'm going to draw that as this curly thing here. This is the filament. You heat it up using a power supply, and it gets so hot that some of the electrons in the outer layers of the atoms that make up the filament can actually escape the surface and become free. And so then it says it is attracted toward the positively charged anode. So what you do next is you have, let's say, a set of parallel plates that looks like this, and you charge these up so that one side is negative and the other side is positive. You cut a little hole in here so that the electrons can drift in, and when they do, they go from the negative side, they get accelerated to the positive side. They experience a force this way, and they gain kinetic energy, losing electrical potential energy. They tell you that the potential difference is 20,000 volts, which is a very large number, of course. I'm going to write that in there, 2 times 10 to the 4 volts. Okay? And the question is this: what is the speed of the electron when it reaches the positive plate? Now, a couple of assumptions here. We're going to assume, rightly or wrongly, that the kinetic energy of the electron is equal to 0 in the beginning. Of course, the electrons have to be moving in order to enter the parallel plates or the cathode ray tube. However, they can be moving relatively slowly compared to what's about to happen to them. Now, let's talk about whether we should use forces here or whether we should use energy ideas here. You can use forces for the reasons I explained. They do give you the delta V, but they don't tell you the delta D, the separation between the plates. So I'm actually starting to think, maybe I won't use force ideas here. Maybe I'll think about what I had here, the energy idea. Remember this, that the negative change in kinetic energy is equal to the positive change in EE. Let's see how that works. I'm going to write this out. due to the law of conservation of energy, negative delta EK equals positive delta EE, or if you prefer, put the negative on the other side. Doesn't really matter. What's this going to give us? Negative of EK final minus EK initial is equal to delta EE. Now, are you tempted for delta EE to use this formula? KQQ over R? If you are, you're going to run into trouble. Why are you going to run into trouble? Because this formula here is for 2-point charges. When we know that there are 2 charges only, and they are exerting forces on one another, and there's potential energy, we can use this. That was the case back here. There were 2 charges. But what's going on here? Oppositely charged parallel plates come with many, many, many charges all along the surface of them. There are countless charges on both plates. I hope you're not about to start calculating the electric potential energy due to each of those charges on this lonely little electron. It would take you a long time. So we need to use another idea. Do you remember another formula for delta EE? Pause the video, go back, look on your equation sheet, do whatever you have to. I'll give you a hint, section 7.4 in the textbook, to find a formula for delta EE. All right, you're back. What did you find? It's Q delta V. If you remember, Q is in coulombs, and delta V voltage is in joules per coulomb. And so that cancels out. Coulombs goes with coulombs. You get joules, which is what kinetic energy is, which is what electric potential energy is. So, a couple of other things. We are assuming the initial kinetic energy is 0. So what's this going to give us in the end? Negative EK final, which of course is a half mv final squared, equals Q delta V. Now, are some of you worried that we're squaring speed here, but there's a negative, and you're worried that when you take a square root, you'll have the square root of a negative number? Well, watch what happens. Let's think for a moment. First of all, the electron has a negative charge. So what are you going to sub in here? You're going to put in negative 1.6 by 10 to the negative 19 coulombs. That negative is going to take care of this negative so that you don't have to kind of, when no one's looking, erase this little negative sign. A lot of students do that. They see a negative sign they don't like, they scratch it out. That is just bad math, it's bad physics. You know you're doing something wrong. It's like stealing from the cookie jar. You don't have to do it. If you're paying attention to your charges, things will work out for you. What about delta V? We are going from a negative potential or negative plate to a positive plate. When any number goes from a negative to a positive value, the change is positive. So all we got to do here is sub in the negative charge, the positive 20,000 volts. The mass of an electron, you are going to have to look that up. What is the mass of an electron? Look it up. Don't ever forget it. It's a really tiny particle. It's a really small mass. And then you can solve for V final, and you'll see that the electron gets going quite quickly. And the idea in a cathode ray tube such as used in a computer terminal or an oscilloscope is that we accelerate the electrons toward the screen. Of course, you're over here sitting at your desk watching TV or the screen. When the electrons hit the screen, they hit a phosphor coating. This is a chemical where when you whack it very hard, when you whack the atoms in there very hard, they become excited, their electrons go to a higher energy state, and then when the electrons drop back down to the original energy state, they give off light. And the light which comes to you is what you see on the screen. All right? I'll leave it to you to finish this one off. I'm going to finish up with one final question, and here finally we're going to use force ideas for real because the situation will call for it. This is basically the idea in a cathode ray tube. It's sample problem 3 from your textbook, Physics 12 by Nelson. Before we do this one, a couple of things that you got to know. There's an electron that is this time flying through some horizontally oriented parallel plates, unlike what I described to you back here, where the plates were oriented this way. So the setup is a little bit different. it says that the electron is fired at 2.5 million meters per second into these parallel plates. Question, how did it get going this fast? Answer, by doing this to the electron. I should have mentioned before, we have a name for this kind of apparatus, the device that accelerates electrons to really high speed. It's known as an electron gun. All right? And this is a component of a cathode ray tube that you would find in your computer terminal. First, we got to get those electrons moving, but then we're not done. If we just get them moving, they're going to go forward and hit the screen. They're going to make a little dot of light in the middle of the screen, and it's going to be a very boring viewing experience for you. So how does the television or the computer terminal or the oscilloscope really work? Let me show you an image that I pulled off of Google Images, which gives you a better idea of this cathode ray tube. Back here we have the electron gun. We just described what was going on. Here's your cathode and your anode. The electrons are being accelerated in this direction, losing electric potential energy, gaining EK. We discussed this. This was sample problem 2. Go back and look if you want to see. But now, here's the screen that I was talking about, and here you are sitting watching your TV or your computer terminal. You don't want to see just a dot in the middle where the electrons would go if we just let them fly straight to the screen. You want to deflect them to different places on the screen to sketch out different patterns so that we get an image. After all, that's basically what TV or computer terminal is showing us. It's just showing you an image drawn electronically. So we have to deflect this beam to a vertical and a horizontal position on the screen. Let's say this is maybe the x-axis horizontally, and this is the y-axis vertically. Where do we want the image, the light, to go? Well, we got to deflect some combination of vertical deflection, so we have what are called vertical deflection plates, and this is what sample problem 3 is about. I'm going to do this in a moment. It's right here. And you also need horizontal deflection plates right here. We don't have a sample problem for this, but it's really the same physics as sample problem 3, so I don't need to do both. This is how we're going to get the image we want on the screen. All right, so let's go back here and let's take a look at what's going on. The electrons moving into the parallel plate apparatus, the horizontal parallel plates, it says they are 7.5 centimeters in length. I'm going to draw that in right now before I forget. I'm going to convert to meters as well. Now, this is a horizontal distance, so I'm going to call that a delta dx, like that. At this high speed that these electrons are traveling, they will not spend very much time in between these parallel plates. They tell us that the electric field has a magnitude of 130 newtons per coulomb. Remember, electric field is uniform between parallel plates like this, and it's the direction that a positive test charge would be forced. Since this is an electron, this electron will actually experience an upward force. So I'm going to draw that in like this. This is the electric force, and as you recall, in a constant electric field, we can just write Fe equals Qe, just like we write Fg equals mg, if this were a gravity question. It says that the plate separation, so that's this vertical distance here, is great enough to allow the electron to escape. What do they mean by this? Well, let's think for a moment. The electron is going this way, and it's going to experience a force upward. Have you ever seen a situation where this happened, where an object moving horizontally entered a force field that was perpendicular to its motion? I'll give you a moment to think. You've got to think way back to the beginning of the course for this one. See if you can figure out what it is we're talking about. Okay, you're back. 2 thoughts that may have entered your mind. Thought number 1, you may be thinking that the force and the velocity are perpendicular, and therefore you might be thinking uniform circular motion, centripetal force. If you were, congratulations, it's a great thought. However, it is actually not quite correct, because here's what's going to happen here. As the electron moves into the parallel plates, it's going to experience a force up. So it's going to begin deflecting. It's going to get pushed upward, but it's also going to start to gain a little bit of vertical velocity. So very soon it will begin to accelerate in the y direction, even as it continues in the x direction. This means it's going to have a y component of velocity, which I'm going to write as vy, and it's going to have an x component of velocity, which I'm going to write as vx. There is no force in the x direction, so vx is constant. There is force in the y direction, so vy is changing. There is acceleration. If you add these two velocity vectors together, you get a combined or a net or a resultant velocity that looks roughly like this. This is what we call the instantaneous velocity. Now, this means the electron has moved a little bit on a curved path, but it's not a circular path because now the force is still vertical, like this, but the velocity is now not 90 degrees to the force. So if you were guessing uniform circular motion, that was a great guess. It means you're really, really connecting things. Good guess, unfortunately incorrect, but that's how we learn, by guessing and checking. What is going on here? What's the other thing that this could be? If you guessed projectile motion, you are correct. What's going to happen here is the exact same kind of physics, just with an electric field, same kind of physics that we had with a gravitational field when we did the following. Remember back at the beginning of the course, we launched a ball horizontally with a velocity vx. Due to the force of gravity, there was acceleration in the y direction, and we did our projectile motion. This is a constant force because of the nature of parallel plates, and therefore we are able to use kinematics. So this is another example where force is, an option. All right, what do we do here? Well, first of all, let's analyze some things. Remember I said that the electron is moving so fast it won't spend a heck of a lot of time between the parallel plates. Remember how I said that the x velocity is constant and here's the x displacement? How long will the electron spend in there? Time is equal to distance over speed, when your speed is constant, 0.075 meters at a speed of a pretty impressive 2.5 by 10 to the 6 meters per second is going to give you a certain time. In that time, what is going to happen? Well, Vx is going to stay constant at 2.5 million meters per second. So we can just write that in. Knowing that the electron was moving initially horizontally, it says it was fired horizontally, we know that V1 in the y direction is 0. However, we also know that there is vertical acceleration. What is the vertical acceleration equal to? Well, it's equal to the net force in the y direction divided by the mass. What is the net force? Well, pause the video for a moment and see if you can identify what makes up the net force, and then come back. All right, you're back, and what do you got? Well, definitely Fe is one of the forces, but what about Fg? Isn't this happening presumably on Earth? I mean, that's where we have cathode ray tubes, right? Shouldn't we also include Fg? Question mark. Hope you can see that on your screens. Well, if you want to know, then do the following. For an electron whose mass you looked up on a previous question, you'll now know that it's 9.11 times 10 to the negative 31 kilograms. And if we calculate mg, we get a very, very, very small number. If you calculate Fe based on QE here, you'll see that it is many, many, many times greater, like literally billions of times greater, more than billions, trillions. I don't know the number off the top of my head. You could calculate them. I haven't done them yet. But you'll see many powers of 10 larger. So we can actually neglect gravity here. We don't have to calculate its force. It is dwarfed, it is overwhelmed by the electric force. So getting back to over here, Fnet is really just going to be Fe. and that will be QE over m. So what do we got here? 1.6 by 10 to the negative 19 coulombs times 130 newtons for each of those coulombs. That'll give you newtons. Divide by 9.11 times 10 to the negative 31 kilograms and find your acceleration. Now what have you got? You've got v1y, you've got acceleration. From these two, you can find v2y because you also have time. v2 in the y direction equals v1 in the y direction plus a in the y direction delta t. Is this all coming back to you now? I hope it is, because you need to study this at the end of the course for the exam anyway for projectile motion, so now you're killing two birds with one stone. What were they asking us? Find the velocity of the electron as it escapes. That means to find this, the instantaneous velocity made up of Vx and Vy as the electron follows its curved path and emerges from the parallel plates. Remember they said to assume that the plate separation is great enough to allow the electron to escape. All that's telling you is that these plates aren't so close together that the electron crashes into the upper plate before escaping. Anyhow, how are you going to finish off here? Let me carve out a little bit of space. There we go. You're going to know v2 in the y direction. You know vx, which is constant. So what are you going to do? You're going to put them together. I believe I was using red for vx. That's going to stay the same. You will have calculated vy. That's going to look like this. They, of course, are by definition at a right angle. And finally, you're going to use Pythagorean theorem to calculate the instantaneous velocity at a certain angle upon escape. So use Pythagorean theorem for the magnitude, use trig to find the angle, and then you'll be done. All right, folks, that's it. 3 good questions that deal with the motion of charged particles in electric fields. No fact of the video today because we really weren't learning anything new. We were just applying old information. But please make sure you know, when can you use force ideas, when can't you? When do you have to use energy ideas? When can you use the point charge formula? And when do you have to use other more general formulas like this? All right, if you can answer all those, then I think you've got your bases covered. All right, thanks for watching, and I'll see you guys in class. Take care.